Privacy in the Overparameterized Regime by Simone Bombari from ISTA. Please go ahead.
Thank you. Thank you. Thank you, everyone, for joining. I will join the other speakers in thanking all the organizers for setting up, again, this amazing workshop. Very happy to be here. Today, I will talk to you about some work joined with Marco Mondelli, also, as you know, in the audience. Let's jump into it right away. This is an agenda of this talk. So this is a talk about privacy, and I presume a good portion of the audience is not very familiar with this topic. So I will definitely dedicate enough time in introducing it and explain how to obtain this in deep learning. And then I will also try to transmit some concepts like what is the cost of privacy, both in practice and in theory. And then I will move in maybe more pop culture topics like overparameterization and random features model. At that point, I will be ready to state our main result. And then, also depending on the time, some proof ideas, some numerical evidence, and some comments on future work. Please feel free to interrupt at any time. I'm also very happy to keep this presentation as interactive as possible. OK, so what is privacy? This, I think it's a pretty open-ended question, almost philosophical. We are a few days late to discuss about this. So I would rather give you an example of what is not privacy, especially with a cartoon that comes from the machine learning experience. And the story is the following. You have a machine learning engineer friend that really needs a lot of data to train their model. So you're their friends, so you lend them some photos of yours, X1, which without a sensitive photo. These are photos of yours that you wouldn't really want other people to see about yourself. But maybe a machine learning model, you're fine if they see them. Then this friend of yours uses a data set containing this image to train a model. So they will obtain this parameter theta star in R to the P. And then this friend of yours is going to trash completely the data set D. It will simply deploy theta star. So apparently, you're safe. You're not going to have any problem because the data set has been canceled. But it turns out that some magical people implemented some magical method that starting from theta star, so the parameters of the model alone, they were able to recover training images, training samples. So this has been done practically both in natural language processing and computer vision. I'm citing two, let's say, seminal works by Carlini, Haim, and collaborators almost 3-4 years ago. So yeah, 4 years ago, we were still at GPT-2. And you see that via some nicely implemented prompting strategy or via some optimization methods, you can either reconstruct some personal information that here was purposely redacted in their paper about some individual. This comes from the pre-training data set. Or images from, this is simply CIFAR10. They trained some neural networks on CIFAR10, and they were able from the parameters to reconstruct the images. I think this is pretty magical, the idea to go from the training to the model parameters to the training images. And this is possible. So the pointer is not. OK. There were some battery issues with this before. So the arrows of my laptop work. So worst case, I can simply go with that. Any questions so far? Yes? This is a great question. I think in general, yes. So for example, very simple strategy that is not going to work on ChatGPT, but my work on other models is that you prompt, hi, I am Simone Bombari. I really like to, and eventually the model will follow this because maybe this sentence was in the training set, so there is a high likelihood that the next token will be what was in the training set. So you can warm start your approach to target something specific. I will go with the arrow. Yes? OK, so let's say you recovered this, and you wonder if this was indeed in a training set. I would say the perspective of this work generally is not. So they get something, and then since these are controlled experiments, they know that this was in the training set. So they say, aha, we found something. So, and this is concerning enough, that might say, attacker will find something. If they publish it, maybe this is meaningless. So yeah, no one is going to care, but it might be meaningful, okay? So again, one solution to this problem is you simply do not give your data to your friend, but then maybe this person is not going to be your friend anymore. So maybe you can agree that maybe there is a magical algorithm, a magic, such that 0.3 is not possible. So this is going to be probably impossible that you can reconstruct information about the training data. So it turns out that such magical methods exist, and these belong to the framework of differential privacy. This is something that has been pretty much around for the last 20 years. I'm going to go through the definition with you. I'm going to go on this side because I think speakers tend to go in there, and I'm upset about this side of the audience. So an algorithm A satisfies epsilon delta differential privacy is if for any pair of adjacent data sets, adjacent means that D is the original data set, and D prime, you can think about the identical data set without your photo. So there is a Hamming distance 1 between these data sets. So for any pair of these adjacent data sets, and for any subset of the parameter space, you have this probabilistic inequality. This probabilistic inequality might be scary at first, at least it was to me. So let's look at some corner cases, like where epsilon and delta are both equal to 0. Okay, this inequality is, of course, parameterized by these two numbers, epsilon and delta. So if these two numbers are equal to 0, since these probabilities are also normalized, you have that P of the algorithm used on D and P of the algorithm used on D prime converging in some set is identical for any set. This is perfect privacy because it's telling you that if the model was trained on a data set or on a data set without your photo, nothing would have changed. So if this is the case, then you're pretty much safe that your photo is nowhere in the weights of the network. On the other hand, you can look at epsilon equal infinity or delta equal to 1, and you're basically enforcing nothing. So this is no privacy. For the sake of this talk, we will consider epsilon of order 1. You can think about the epsilon equal to 1, and delta equal to 1 over n. In some works, this is what sometimes is dubbed that good level of privacy. I'm not going to enter the details of why this should be good. This would open a big topic. Just be aware that this epsilon is not just a number. It means something. And here, for example, there is an example from an attack in this paper where they want to reconstruct this image, which is a target. And in data reconstruction for that attack, you see that the transition of non-success and success is at the level of 10 to the 3, 10 to the 4. And there's also some converse results in this paper that says, okay, if you're interested in data reconstruction, that you need an epsilon that is considered safe is an epsilon which is smaller than the number of pixels. If instead you're interested more in recovering a single bit, so was this image in the training set or not, then maybe you're more interested in epsilon of constant orders. But depending on the threat model, you might be interested in different things. Ah, awesome. I did it on purpose. I just wanted to check if you were paying attention. This is the number of training samples. So the more training samples you have, the smaller you would want this term to be. And in practice, sometimes, for example, MNIST is very common to see 10 to the minus 5. So, again, these are heuristics. And in general, you fix an epsilon, you fix a delta, then you test with some attacks that you consider the things you're scared of, and then you see what happens. And that would tell you what the epsilon you want. There was another question? Thank you. OK. Great. So you tell your friend that there is a magical algorithm that they can use to implement privacy, but what is this algorithm? So let's go through gradient descent. This is probably something that everyone in this room has seen at least twice. And this is going to allow me to introduce some notation. We initialize a network. We fix some number of iterations, a learning rate. And then at every iteration, we compute the gradient with respect to a loss on an individual image label sample. Then we aggregate this gradient. We divide over n, the number of training samples. And then we perform a descent proportionally to the learning rate. We do this t times, and ideally, the output of this algorithm is going to give something that, I don't know, has optimized or generalizes well. Now let's look at the PGD. This is the private version of this algorithm. It's pretty much similar. So we, again, fix number of training iterations. We compute these individual gradients. But before aggregating them, we need to do one critical step, which is called clipping. That means that you take a gradient. If its norm is larger than a clipping constant, which is a hyperparameter, you reduce it up to this number. So if you have a gradient, let's say that this is a ball, the radius is the clipping constant. If you have a gradient that is like this one, you do nothing. But if you have a gradient that is like this one, you have to reduce it such that its norm is at most the clipping constant. Once you do this for every per sample gradient, you can aggregate them. And after you aggregate them, you can do your descent, like in gradient descent. But there is one more step, which is adding some noise. Notice that this noise is proportional to the clipping constant and proportional to sigma, which is another hyperparameter of the algorithm. This looks a bit scary. It looks also a bit arbitrary. But there is this nice result by Abadi, 2016, that tells you that if sigma is sufficiently large, so you add sufficiently large noise, notice that this noise depends itself by the number of training iterations, then you can achieve epsilon delta differential privacy. Of course, with the noise that depends on epsilon and delta itself. So allow me to remark, smaller epsilon, more privacy. I will forget mentioning delta at this point because delta impacts this algorithm only via a logarithm with respect to n, because we're going to set delta equal to 1 over n, and I'm not going to care about logarithms in this talk. OK. What do we learn from this as well? That if we want smaller epsilon, there are mainly 3 things that we can do. Reduce the number of training iterations, or increase the gradient noise, or reduce the clipping constant. This may be a bit vague, but notice that if you keep constant both epsilon and the overall amount of gradient noise that you're adding at every iteration, this also implies that you can achieve this with smaller clipping constants. Okay? These 3 things are tied together. Eventually, you're going to need to work on all of this. This is going to be the optimal hyperparameters to achieve the privacy performance. Any questions? Yes? Of course. There's going to be a trade-off. The more privacy you want, probably the less you're going to be able to learn. And thank you for the question, because I think the best way to understand how private optimization works is to do some homework. I of course, do not have the time to make you open your laptops and run some experiments, but let's do this together. So we're going to do something very simple. We're going to train a 2-layer neural network fully connected on MNIST with the PGD. Cross-entropy loss, learning rate is 0.1, width is 100 on 50,000 images. This is probably the first experiments you should run if you want to learn about the PGD. Let's do this first with epsilon equal to 1, the clipping constant equal to 10, and the number of training iterations equal to 100. Notice that since I fixed epsilon, clipping, and t, this is going to determine the value of sigma, right? What you see, I'm plotting the train and the validation error. As the epochs follow, these together go down. But what I see from here is that maybe if I went a bit longer in the optimization, this could have gone lower. I'm achieving something like 90% accuracy here. Not super impressive with MNIST, so maybe I can do something a bit better. So let's fix epsilon and clipping constant, but let's increase the number of training iterations. As we do this, we see something maybe a bit surprising, which is we get something less performant. So the optimization plateaus and does not achieve any more 90%, more or less. Does anyone have a guess why this happened? Too much noise. We are paying fixing epsilon, increasing the number of training iterations, we're adding more noise. That screws us. So let's go to another panel. Yes? Why aren't they identical? The more t, I should have, for a fixed epsilon, a fixed clipping constant, if you have more epochs, allow for more epochs, at every iteration, you need to add more noise. So even in the early stage, this is going to be more corrupted.
Yeah, got it. Okay.
Great point. Okay, now so probably it's not very smart to increase the number of training iterations at this point. Let's try something different. So I'm going to consider t equal to 100, but I'm going to decrease the clipping constant now, always with epsilon equal to 1. And we see something, in my opinion, complementary to what we had before, which is simply the optimization is too slow. We're not optimizing enough time. The clipping constant is too small. If the clipping constant is too small, we're effectively reducing the learning rate. So we simply do not have enough time. So let's go again on the right, increase the number of training iterations. That's great. This really looks much like the top left panel because we give more time, so we can optimize. And again, if we increase furthermore the number of training iterations, t here is equal to 10,000, we have the same problem. Okay? This is shifted because smaller clipping constant, less noise, but more time, more noise. Is there anything suspicious in these plots that anyone want to point out? So the first thing that I noticed that made me look for if there is any bug in this code is that the training and validation error of these plots overlap almost completely. So either there is a bug in my code or this makes complete sense, because if we are respecting privacy, there is no way we can distinguish training images from test images. Otherwise, we would have a method to identify an image as, this was in the training set. But since it's privacy, we cannot do this, and in particular, the test loss, here, of course, it's an average, but even point-wise, they should look alike. So enforcing privacy implicitly is making validation performances and train performances being the same. In the sensitivity check, I have exactly one empty panel here. So I'm going to use epsilon equal to 1,000. And now I'm going to do the two things that were screwing me before. So I'm going to take a large clipping constant and large number of training iterations. So I have all the time in the world to converge. And now you see something nice. So you see that the validation accuracy increases. So sorry, the validation error goes further down. And you also see the splitting between training accuracy and validation accuracy. Yes? No. Okay, yes. Implicitly, I think I'm making that assumption. So what I gave you before with this intuition was not a proof. It was more of a hand wave. I hope that you agree with me that if consistently on training images, my accuracy is higher than on validation images, then there should probably some images for which the accuracy is too high, the model is too confident. That should suggest that these are training images rather than test images. With gradient clipping plus early stopping plus noise, we have privacy. I'm assuming the theorem from a body. So if you believe in me that this gives you privacy, privacy should give you this. Okay, yeah, all the things have to be together. And here, just to conclude the argument from before, here we see a clear example of the moment where we are actually overfitting the training images. So the training error is going to be lower than the validation error, but this overfitting is nice to us because also the validation error is decreasing. So we're happy. So hopefully by now you understood that there is a clear trade-off between accuracy and privacy. If you want privacy, you might not be able to achieve accuracy. And to give you also an example, I'm giving you these results from the paper by the Entholen 2022. Look at the blue line. This is test accuracy on CFAR 10. For epsilon equal to 4, they get 75%. This is way less than what you can get in the non-private case. And this was a massive experiment. This paper is from Google DeepMind. And as far as I know, for epsilon equal to 4, this is the current baseline on CFAR 10. Furthermore, notice that private optimization can be also a bit more expensive. You need to instantiate every per sample gradient. You have to clip them before aggregating. On average, it's going to take longer to optimize. And if you also count the fact that you might need to optimize over more hyperparameters, that's even more painful. So private optimization is painful. This is another thing I would want you to bring home from this talk. OK, so remember, there is this trade-off. It's painful, and there are three ingredients that are screwing us: early stopping, clipping, and gradient noise. This is what we have to fight with if we want to optimize it privately. Great. Let's go back to theory. I'm going to remove my engineer hat. These trade-offs have been studied in theory, and people are looking at what they call the excess population risk. So they consider a non-private baseline, theta star. You can imagine this as, for example, the solution of gradient descent, so a non-private algorithm. And you can see how higher is the population risk of a private algorithm with respect to the population risk of the non-private algorithm. This is exactly what we were testing before with the blue and the red line. Sorry, not really. Yeah, maybe in the epsilon equal to 1,000 case with respect to epsilon equal to 1 case. And there is a clear trade-off. This is the trade-off between privacy and accuracy, and this trade-off has been very extensively studied in the last decade. People gave upper bounds and lower bounds on this quantity, and generally these bounds depend on epsilon, the privacy parameter, p, the number of, epsilon is the privacy budget, p is the number of trainable parameters, and n is the number of training samples. Just to give you two examples to make you realize what I'm talking about. One case is Lipschitz convex bounded optimization. We have this result by Basile et al. In 2019. These are both almost tight. And also for linear regression, there are equivalent results. P here corresponds also to the ambient dimension, because in linear regression, number of parameters is equal to the input dimension. Notice, informally, you have that the epsilon is at the denominator. This makes sense, because if you want more privacy, epsilon is going to be smaller, and as it's smaller, you have to pay more in the excess population risk. I'm going to switch away from privacy for one slide. I'm going to talk to you about overparameterization. This is maybe something that more people in the room have prior background on. Informally, what do I mean by overparameterization? I mean by the regime where the number of parameters is larger than the number of training samples. And here I'm putting one example of many successful papers that in the last 5 to 10 years made us understand why such a regime could be beneficial for us in deep learning. And here I'm mentioning the paper by Misha Belkin, where you have the standard variance bias trade-off. So you expect that after some sweet spot, more parameters might hurt you because you have overfitting. But almost magically, it turns out that in some regime, in some cases, as you increase more and more and more the number of hyperparameters, the number of parameters, the test risk is going to decrease. And you have this double descent curve. And what happens here is what we want to have when we use larger and larger nets. And there are concepts like double descent, benign overfitting, and things that try to explain, statistically speaking, why this happened. More formally, you can imagine to have a two-layer neural network, maybe just out of benefits for the theoreticians. You can imagine that the first layer is random. You're only training on the second layer. And for some data distributions, in some cases, you can recover this curve exactly in the limit. And I'm mentioning at the moment the paper by Song Mei and Andrea Montanari on random feature regression and the double descent phenomenon. So let me remark again. P is number of parameters, N is number of training samples, and D is the input dimension. For the sake of this talk, imagine P always larger than N, and N you can imagine to be of the same order of the or a bit larger. I'm going to be more specific later about what our main result does. Let's go back to privacy. So this is taken from the previous slide. We said that we have this quantity, excess population risk. We are interested to understand what privacy optimization is going to do. And these bounds on the excess population risk depend on epsilon, p, and n. And it turns out that if you test the bounds provided at prior work, in the regime where p is larger than n, all the existing bounds give excess population risk of order 1. Notice that this is vacuous, because a model that constantly outputs 0 has the same generalization guarantees of this. So this tells nothing. I've been purposely not super specific on which model in this regime you should test this. Ideally, you should test this on every model, but what we do is mainly variations of the random features models. So you might think that I'm a bit biased towards evaluating these bounds, but this is actually something that the community is aware of, the community of differential privacy. This generated what we define a common wisdom. This is also explicitly mentioned in prior papers, also on lecture notes on differential privacy, that differently from the non-private case, in private optimization, you have to add noise. Since you add noise in p dimensions, the more dimensions you have, the more noise you're adding, and that's going to be bad for you. So this lack of theoretical results also brought people to propose algorithms that effectively lie in lower dimensional to try to add less noise. Okay, but now the question is, okay, do we really believe in this? Do we really believe that all the results on benign overfitting and the effect of overparameterization hold only in the non-private case and not in a private case? And this is what we're testing with this experiment. So we do an experiment with the same model we had before. So neural networks, MNIST, very, very easy. But instead of varying the hyperparameters, I'm varying the width of the networks. And for every model, I'm finding the optimal hyperparameters to maximize the validation accuracy. And then if I see that for wider networks, the performance is decay, then I might say, okay, the best hyperparameter selection on larger models is worse than for middle models. So maybe these folks are right. But this is not what we see. So the performances plateau with number of parameters, and they do not pretty much down when the number of parameters is 100 times more than the number of training samples in MNIST data. Any complaint? So you might, okay, I'm not the only one realizing this. In the paper I was mentioning before on baselines also for CIFAR10 and ImageNet data, this is how actually they got the state of the art. They achieved the state of the art with larger and larger ResNets. So what they point out in their paper is that they do not see this problem of using larger models. Of course, using larger models is going to be more expensive, but the highest performances are achieved for indeed larger models. At least here, they compare two ResNets, and the wider and deeper one succeeds for epsilon, at least 3, and so on. And this is where they achieve the baseline with respect to other work. And if you believe that somehow theory should be predictive of practice, you should be annoyed at this point. It's clear that there is something missing here. Yes? DPGD. So in here, it's as pure as in the second slide. In here, they do a bit of batching. They do a bit of layer normalization. So there is a bit of engineering here. But their point is also is that it's the minimal level of engineering on top of DP SGD with large batch sizes. And they do not rely on any dimensionality reduction like the other paper I mentioned before. What they rely mainly on is scale and very fine-grained hyperparameter optimization. Okay, so at this point, I think the only thing we have to do is to take a very simple model that allows us to investigate the effect of overparameterization, and I do this with random features regression, which is probably the easiest model one can use for this purpose. This is a 2-layer neural network with an activation phi, some Gaussian weights v, which will not be trained, and the training is also only going to happen on theta. So this is effectively a linear model. This model has been extensively studied in the past in the non-private case, and I'm mentioning 2 papers. Again, May Montanari in 2022 and more recent paper on the polynomial regime. Here is what I was mentioning before, the nice and sweet double descent curve when the number of parameters increases with respect to the number of training samples. This one more sheds light on the sample complexity of using this model for different tasks. So here I'm increasing the number of training samples with respect to the input dimension. And you see that as you cross polynomial barriers, you improve the performance. And the people that are pretty much interested in feature learning are because this is not so exciting because if you have a linear number of samples, you're still bounded and you cannot learn, for example, single XL models. But for the sake of this talk, I'm happy with these performances. These are going to be the baseline for my non-private algorithm. And simply, now at this point, we simply run DPGD on this model. This makes me ready to state the main result. This is informal and says that let's take a solution of an epsilon delta DP algorithm for a proper choice of the hyperparameters. I'm not going to mention them here, but this is constructive, so we give these hyperparameters for all sufficiently overparameterized random features models. this is what you get with high probability. This is a bit nasty, but imagine to have epsilon, wow. Imagine to have epsilon equal to 1, and n just much larger than d, so let's say d to the 1.1. This goes to 0. This vanishes. This means that in some regime, in particular when n is between d and d to the 3 divided by 2, and when epsilon is sufficiently large, so you're not asking for insane level of privacy, you can actually achieve privacy for free. There is no dependence on p. We require a lower bound, which is p is larger than n squared. I do think that this can be improved to simply n, but this is not what we formally have in the paper. And the technical condition is, if any of you is interested, we assume something on the Hermite coefficients of the activation, data is on the sphere, concentrated, and the learning rate is sufficiently small. Okay, this should puzzle because we learn, especially from our experiments, that there is a price to pay for privacy. So either I'm lying or something is going on. So let's look again at the result. What's the intuition? If we look at the non-private performances of a random feature model, we see that when n is between d and d squared, the performances are plateaued. So in this case, adding more samples does not improve the performances of the private algorithm. Okay? So what does this mean? This means that we have a surplus of samples that we can be used to learn privately. Or in another way, when we have n larger than d, like d to the 1.1, we do not really need to look too closely at every sample because the task is easy enough that we do not need to rely on any individual of them. And that's why we can achieve privacy, because we do not need to focus on any of them. This is automatically between the lines done by gradient descent, DPGD. This may sound a bit an artifact of how the random features model behaves, so let's try to get this intuition also from the MNIST dataset. What do we have? Let's plot in blue the solution of gradient descent. So this is non-private. And let's play with increasing the number of training samples. So as I increase the number of training samples, I also should see the performances to increase. And we see this happening very fast when the number of training samples is between 10 and 1,000. So on the MNIST dataset, if you have 10 samples or 1,000 samples, it makes a big difference. But it doesn't make a big difference if you have 1,000 samples or 10,000 samples. So I claim that this right part of the plot is the part of the plot for, in the MNIST task, you have more samples than what you actually need. And this is also the part where you see the performances of the private algorithms. Here I have 3 levels of privacy, increasing sharply, and then actually approaching pretty closely the ones of MNIST. MNIST is a sufficiently easy task for the number of images that you have, where you can effectively achieve privacy here almost for free, simply because this gap is much smaller than what you have here. This is more realistic. This is what you would find, for example, in CIFAR 10. And what our result is about is that all this intuitive pictorial narrative holds for any model of any size. So the number of neurons is order of 1,000, so the number of parameters for any point of this plot is much larger than the number of training samples. This concludes the main result. I might use some of the remaining time and give some high-level proof ideas. Yes? That's a great point. So that, in part, is something that probably could be done better in the proof. I would expect that to be more something like d over n plus n over d squared. Why? Because these are the critical points where this intuitive effect of having enough data does not hold anymore. So that's saying, okay, if you're in the middle, you're good, but if you're not, then you're gonna have some problems. Yeah, the 3 divided by 2 is also another place where this could be improved. Okay, I will increase slightly the pace, and I will give you some proof ideas. How do we do this? First, I like to deal with continuous processes rather than discrete. So I want to frame DPGD as a stochastic differential equation. So I define an auxiliary loss function, which is the Huber loss, that is quadratic close to the origin and then linear. And it's pretty easy to see in this setup that running these gradient descent plus noise on this loss is equivalent to running the original DPGD. Then at this point, this is exactly the Eulero-Maruyama discretization of this SD. And then I simply have to study this SD and compare it, for example, with the cousin, non-private cousin, which is gradient flow. And here, again, I stress in yellow, blue, and red the fact that we have clipping, that we have the noise, and that we have the early stopping there. So how should we set the clipping constant? We would want to solve in closed form this stochastic differential equation on that potential, on that loss, which is clipped. And I'm not super happy about this because I don't think I can do this. I would be able to do this instead, where I replace the loss with the original quadratic loss, because this is a Brownian motion in quadratic potential. This is a Ornstein-Uhlenbeck process. For the ones that are a bit familiar with this is pretty much solved. We would know everything, the probability distribution, many things about this process. So heuristically, this suggests a proof approach, which is setting the clipping constant so large, so the part of the landscape that is quadratic is so huge that I'm so sure that during the optimization, I will never cross this boundary. So I can simply solve the problem in the quadratic case. Does anyone see the problem with this approach? You have to make the noise larger. The more the clipping constant, the more the noise you have to add at every step. And that's going to screw you. So yes, this is why this idea is terrible. So maybe a better idea is to set the clipping constant just large enough. So we have the same proof approach, so we can solve this SD, but we need to be very, very precise. We cannot give more than what we should. And this is one of the biggest technical contribution, which is about finding this clipping constant. Here again, I'm happy to give for free some logarithm factors such that all the optimization happens within this boundary. For people that are familiar with first heating times and these diffusion processes, this is pretty much what's going on here. We do not want this Brownian motion to hit the boundary of Curly C. Okay, now that we have the clipping constant, we need to set something else. In particular, we need to set the early stopping time. If we do this, the noise is going to be automatically fixed. Notice that now, since we proved that with high probability we're not going to cross this boundary, we can solve with high probability the solution of the SD on the clipped loss will be, with high probability, the solution of the Ornstein-Uhlenbeck process. But this is closed and can be written as the non-private baseline plus a difference that expresses the effect of the early stopping plus the effect of the noise. So I'm going to study these two terms separately. And I will set the time. I did not properly introduce tau, but tau is simply the number of training iterations rescaled by the learning rate. This happens when we take the limit for the stochastic differential equation. And what we see at this point is that the noise gives this term, which is not bad, which is exactly what we had before. So when n is larger than d and epsilon is equal to 1, this is not a problem. For the early stopping part, the key idea is to resort to the fact that the kernel matrix that also defines the gradient flow equation has a spectral gap. So the training loss, in some sense, decays two-folded. This is in logarithm scale. You wouldn't see this otherwise. But the test loss is already at its minimum midway. So early stopping, if it's not too early, is not that bad. And some people also pointed out yesterday, for example, about its regularization effect. So in this way, we can set, this is exactly, we set this early stopping time exactly in this critical point, and that gives us exactly the three terms. The one that we have from the early stopping, the one that we have from the noise, and the fact that the clipping constant is large enough allows us to connect this to the actual solution of the algorithm. To give you a bit of intuition, I can show you a couple of plots. In the first one, I'm increasing P. In blue, I have the non-private gradient descent, and you see the typical double descent curve. I'm not regularizing here, so at the interpolation threshold, the generalization error explodes. In the private case, you always have this little price to pay, and you do not see any peak. And this is, again, about the fact that in privacy, you're not interpolating. You're adding noise, you're early stopping, so also the connection between early stopping and regularization, L2 regularization, was pointed out yesterday, and that's why everything here is smooth and monotonous. And on the other plot, for example, in the second one, I am plotting for a fixed clipping constant different choices of the early stopping time, and in different colors, different sizes of the parameters. This is random features models. And I see that the optimal points move towards the left. So the bigger the model, the earlier my algorithm is going to converge. And also this suggests why adding noise in higher dimension is not going to screw us, because we gain in terms of time. In particular, if I rescale the time with respect to number of parameters, all the curves collapse into each other. So it's clear that this scaling is clear. I mean, suggests that this scaling makes sense. Two last plots. Let's look at the full hyperparameter space. So on the x-axis, I'm plotting the clipping constant, renormalized by the square root of p. This is more or less the scaling that we propose. And here, the time, again, rescaled by what we propose. So our proof exactly happens in the center of this plot. And you see that yellow is good here. Yellow is low test loss. You see that exactly in this point, you have good performances. If you increase the clipping constant too large, you have this noise problem that we were mentioning before. So here, everything is dark. If the clipping constant is too small and the time is too small, you're not converging. You simply have a model that is not learning anything. But it turns out that, interestingly, there are other yellow points that we simply do not cover during the proof. Notice that a similar profile also happens for two-layer nets with cross-entropy loss on MNIST. So we have always this qualitative aspect of the hyperparameter space. And as I mentioned, aggressive clipping is not a problem. So eventually, this is also close to what is done in practice. In practice, people do not really want to be at the edge of this clipping. They simply set the clipping constant sufficiently small such that they're pretty sure to be in this yellow region, and then they have just to optimize one hyperparameter to cross the yellow region in the right spot. This is not what we study in this paper, but if you're interested in why clipping aggressively is not a problem, we have a very recent work on linear regression with aggressive clipping. This is joint also with Imbar Serussi in Tel Aviv University. I will conclude. So I think the main takeaway of this talk is that overparameterization is not at odds with private learning. Still, nowadays, you might find some papers that propose new algorithms because gradient descent is universally bad because you're adding noise into many dimensions, so you shouldn't use it. Well, that's something I would argue. Of course, the proof here is for random features, but, well, for overparameterization, that's enough for me. And of course, we also believe that our result is a bit restrictive to this regime, but we expect the same conclusion to hold regarding the privacy for free for kernel-rich regression whenever we have these nice kernel concentration properties where we have that the loss does not decrease with the number of samples. Few future direction that I'm pretty excited about. What about learning features? This is something that we're not doing here. What about some theory of this magic of reconstructing images starting from the parameters? This is something we're getting actually very nice visually results, and I'm very excited about. And of course, there are many ways to extend this to, for example, classification, for example, for streaming algorithms, or maybe providing lower bounds to see the effective statistical limits of private learning, scaling laws, and many, many other things that you can think of. Whatever is done non-privately, eventually you can done privately if you're interested. And with that, I conclude. Thank you very much.
Thank you very much, Simone. Are there? Yeah, okay.
Thanks. I have a couple of questions. One, well, it's on your to-do list, so probably I cannot ask too much about that, but do you know what do you expect to change if you have a two-layer network instead of a random feature model?
So very simplistically speaking, if you want to learn some features, one thing that you could do is take one gradient step in the hidden layer that is going to allow your weights to positively align with the, for example, if you're looking at a single index model. And again, if you have sufficiently many samples, you can take this gradient, allow the weights to orientate in that direction, and that's going to completely reduce the optimal early stopping time. Because at that point, the features are so well aligned that the early stopping time I propose here is way, way further than what you actually need to learn at that point. So this is what qualitatively we see right now. If that replies the question. Is this?
Oh, yeah, it does. So you don't expect any real change in your difference between the privacy loss and the optimal loss?
I do expect that if you go in a regime where you have more samples, that if you have a situation where you have more samples than what you need, so let's say single index model and you have n equal to d to the 1.1. So we know that for d to the 1.05, you can learn single index models with this approach. Then in this regime, I would expect that you would be able to do this privately for epsilon equal to 1. Now the question is, okay, what happens when you're in more of a critical regime, for example, a proportional regime? In a proportional regime, it's clear that there is a price to pay in privacy. That's what we do, for example, in the paper with Imbro on aggressive clipping. There, it's more apparent the statistical cost of privacy, which is also something that in practice you really see. So especially for that, that's nice.
Yeah, indeed, this is the other question. So here you are assuming that you have lots of data, but in practice, well, not all, but many of these applications where we are interested in differential privacy, I'm thinking more, I don't know, medical data, you tend to have limited data sets. So now, well, I guess theoretically, probably you should consider the proportional regime as a better alternative. And there, I wonder, how can you do an analysis in that case? How much we pay for privacy?
I totally agree with you. I think especially on a wider purpose level, this is about overparameterization is not going to hurt you. So I'm going to go in a regime that is convenient for me. The regime that is convenient is I have a lot of samples. And here I prove that a lot of parameters are not going to hurt you. So the message I want you to bring home is not that privacy comes for free, because that's never come from free, but that you can use larger and larger models. So in regimes where every sample is critical, that's where you really see the statistical cost of privacy. That's, I think, super interesting. For that, the paper on linear regression gives a bit more insight. And maybe algorithmically speaking, the insight that gives, algorithmically speaking, the insight that this gives is larger models. Larger models are better. The algorithmic insight is smaller clipping constants. So this is, I think, at this point, what we have.
I will give you the mic. I just ask because it's a follow-up of this. So I'm not sure. So if you learn the representation, maybe you said it, but I haven't got it. Do you expect, so at a fixed amount of data and at a fixed model size, do you expect privacy to be harder to reach if you learn or do not learn the features?
I do think that in general, for a fixed privacy budget, the highest performances is where also you learn some features. So if you take, for example, a Gaussian data set with a single index model, and then you fix the privacy budget. In one case, you train a fully connected layer two-layer neural network on both layers. In the other case, you do random features. I would bet that the first one would win. And both are going to bring some statistical costs in terms of privacy, if you consider, for example, the proportional regime. But extending to feature learning, I would believe this to happen. I do not expect surprises. In the non-private case, it's convenient to learn features. And in a private case, it should be. Probably the analysis is tougher.
Yeah, exactly. You encode more about the data.
That's true. So for example, okay, now, is there a corner case for which features, you can learn features non-privately because you memorize them, and then you can learn, let's say, the regression later privately, for which, this gives a non-trivial choice of model for which maybe you prefer random features? I would bet no, but I wouldn't bet all my bank account because we don't have proofs.
Okay. There was one of them. Okay.
This was just a quick comment on this discussion, actually. Like, isn't it in a sense, though, that you learn features when you have the feature? So you've forgotten the training data, but you've learned the feature. So in that case, I would agree that it sort of helps towards the privacy.
So if we think about, for example, single index models, and there, what do we do when we do this gradient step update on the hidden layer? There we want the layer to adapt to this low dimensional manifold. If you have enough data, again, enough data, let's say proportional, slightly faster than proportional, you can do this privately. This can be some sort of thought about, PCA, private PCA. You want to understand some lower dimensional structure in data privately. And there is a lot of literature on this. People want to understand lower dimensional structure of data privately. And I think that the statistical thresholds are really following what we're used to, just with an add and epsilon. But this is very level. I do not have precise answers on this.
Yeah, because now I'm curious. What does it mean to learn a manifold privately?
So let's say that the data, for example, single index models, we saw a lot of sample complexities. That if you have a proportional amount of data, you can learn single indexes arbitrarily well. if n is slightly larger than d. For example, if you have this one, you can learn single index models, okay? Now the question is that, okay, let's say that you have this, and I ask you to have epsilon equal to 1. Can you? And my guess is that yes, you can. Now, if you do this, there is a finite error that you're going to get in the non-private case. In the private case, you're going to again have a private error, which is going to be the same one plus a term that is tuned by the private level. I think this is clear in the example of linear regression. Very easily, in linear regression, you have this error that, you know, the more samples you have, and then you have this term. So there is an additional term. So if you have way more data than D, this asymptotically is going to be much smaller than this. So there you feel that having an epsilon of order 1 is not going to hurt you pretty much. But when, for example, D is equal to n, then you might see that the cost of privacy might be very larger than this, especially if you're asking for epsilon equal to 0.5. So there might be some critical regimes where, in one case, the non-private error costs you more samples, and in the private case costs you less. These are pretty much open-ended questions. I think these sort of problems in the private case has not really been much explored. So there is really a lot of possible future work that one can do, depending on, you know, all the corner cases that one is more interested in, being it feature learning or hyperparameter optimization.
Okay.
Thanks for the talk. I was wondering about the overlapping of training and test error. Mm-hmm. And is it always a good criterion to like understand if learning is private, or are there counterexamples of?
I think it's a good debugging method. So if you're implementing something private and you're saying, oh, okay, the output is going to be 1 epsilon delta differential private with epsilon equal to 1, and then you see there is a huge gap, I would double check the code. But if you ask ChatGPT to produce your code, and then you see that the plots are good, I would still check the code.
So there are counterexamples of overlapping curves, but learning not being private.
Yes, I think you would see this in very outlier cases. Imagine a very regularized method, and you have a data set of tigers and zebras, and there is one white tiger. If you learn that the white tiger is an actual tiger, you're not private, because if you were private, if that image was not there, you shouldn't know this. So maybe on average, you're gonna have same, but then you have to test pointwise. Privacy is really about the pointwise. So if you have average, you don't have pointwise, but if you have pointwise, you have average.
Thanks.
Thank you.
All right, so let's thank Simone again.
Okay.